Thank you. This is going to be a little bit of a different presentation, heavy on the implementation, not so heavy on the math. So I'm interested in resilience to natural hazards, and let's try and put this in the context of this specific workshop, why this is a complex system. Mass migration has led to unprecedented unprecedented urbanization in the last decade, where around 1/4 of the population of the world right now lives in cities higher than 1 million people, and a good 6-7% lives in what we call megacities. Of course, if you superimpose this map with sort of a map of the vulnerability because of floods and hurricanes, or because of the seismic vulnerability, we start understanding that we're putting the majority of the population in very hazard-prone areas. So the expectation is between 2000 and 2050, we will double the population exposed to natural hazards. And so this is, we increase the vulnerability and also we increase the consequences because in these mega cities, the interconnectedness of our infrastructure systems can come and create, effects even starting from very small disruptions. So definitely a very a complex system. In order to address resilience in this setting, you definitely need to talk about different scales, ranging from individual owners to designers and also to city planners. I'm not going to touch across all these scales in this presentation. I'm going to stay primarily up here, and also again I'm going to try to address this problem from the context of data, since this is the focus of this workshop. And for the first part of the presentation, I'm going to focus primarily on how we can use data. So the problem that I'm going to try to address is real-time risk assessment, especially real-time risk assessment for hurricanes. So this is sort of the information that before a hurricane makes landfall, NOAA provides. So some expect but also this cone of uncertainty of how the hurricane can switch. And then we have emergency response managers that understanding, having this information, they try to make intelligent decisions. Sort of our goal is to see how we can help better inform their decisions, starting from this climatological information that a few days before landfall NOAA is providing. Like some quick background on some fundamentals about hurricane risk assessment. In generally, we characterize hurricanes with a small number of parameters that generally correspond to the characteristics during a landfall. Of course, how the hurricane, what the track is going to be, what the variations before landfall is important. But most of the times, we try to address them by running hurricane scenarios that have tracks that are the typical ones that we expect from that region based on historical data. So in terms of parameterization of our problem, this definitely belongs in the low-dimensional uncertainty characterization. Now, in terms of the different models, at least in the US, two are the main models that are being used. One is the SLOS, very computational efficient, but it has huge errors, especially in shallow water, which is primarily where it is in having good accuracy in order to figure out what the inundation zones are going to be. On the other hand, we have AdCirc, exceptionally accurate, so this is what we would ideally like to use. Of course, the challenge is that the computational burden is significant. So a single run of a hurricane track it requires around 1,000 CPU hours. So even with high performance computational resources before landfall, maybe you can run one track, but in trying to do an ensemble of different tracks is impossible. Now the good news is that there are a lot of regional flood studies that perform a lot of these AdCirc runs. So you do have databases that you can use. And of course the idea then is to come and use databases to develop some type of a surrogate model to then be able to predict what's going to be the impact for the hurricanes that are not in your database, and then you can use that in real time to come and help provide real time updated risk assessments to the response manager so that they can make intelligent decisions. And the surrogate model that we use, a little bit before going to the specific database that I'm going to be using in some slides later in the study. This is the most comprehensive flood study that the Army Corps has done for the United States. It's called the North Atlantic Comprehensive Coastal Study. And generally they consider around 595 different hurricane scenarios with some typical characteristic about landfall and sort of the angle with which the hurricane is going to make landfall, and therefore the other parameters like the radius of maximum winds, how big the hurricane is going to be, the central pressure, what's sort of going to be the strength of the hurricane, and also the forward speed. They come and use typical characteristics. So if you come and look, this is sort of the histogram of your 6-dimensional input of the database that you have. And in this case, you are given the database, you didn't have any say about how to develop it. And another point is, this is the case where you have a very high dimensional output because you are interested in coming and providing prediction in a very big region, and also you might want to provide time history predictions. But of course, there is a lot of correlation on this output, especially since you only have 595 scenarios that you can extract data from. So the high dimensionality of the scenario does come and create some challenges, and of course the trick is to explore that correlation with some dimensional reduction approach. In this case, we're going to use principal component analysis to come and reduce the dimension of the output. And you can see that this sort of sensitivity study, the number of latent outputs that you're going to retain through your principal component, and sort of what is going to be the coefficient of determination after you build a surrogate model. You can see that very quickly sensitivity analysis you can reach a plateau, which means that starting in this case from 80,000 output, we were able to reduce it to 25 or 30, and then that doesn't have any significant impact on the accuracy of our predictions. And the memory savings that we can have is 90%. I'm going to come back to these memory savings a little bit later in the presentation. The specific type of surrogate model, we're going to come and use kriging. So pretty much, you approximate the true response as a global trend and a Gaussian process, and like this Gaussian process has some correlation function. So ultimately, sort of like your predictions are Gaussian with some predictive mean that you can very easily come and calculate, and also some predictive variance. And this predictive variance, those of you that have worked with Gaussian processes, you know that there are two components. One is the process variance that actually comes and depends on the observations, and then it's the other component that sort of comes and says what is the variation of your variance in your input domain. That at the end of the day, it depends on sort of the characteristics of a correlation function, but it doesn't exactly depend on your observations. And you can easily come and calculate all this on what the process variance is and all the other features. Now the important key part of any surrogate model is sort of the tuning of the hyperparameters. The two, especially for people that use kriging, two are the main approaches. One is to come and use the common maximum likelihood estimation. So you can come here and write then the likelihood with respect to all the different outputs, the sort of the contribution that comes from each of the individual storms in your database. Now the alternative to this maximum likelihood is leave one out across validation. It has a similar form where now in this case this is the error between your predicted output if you remove that storm from the database and what is the actual output for the storm. And of course the good news is that you do have closed form solution for what this leave one out error is going to be, so you don't have to sequentially come and remove all the storm. Sorry, sort of you do have these two different abilities to come and optimize for the hyperparameters. Generally, maximum likelihood, it's a little bit better behaved, more computational efficient, but we're going to come and see that leave one out cross validation does provide some unique advantages. Another key question is, okay, let's say that if we have certain storms in our database that we want to prioritize for in our optimization, and we're going to come and see later why I want to prioritize some storms. How do we do it? If you come and write your maximum likelihood or leave your not cross-validation in this form, it's very easy to come and incorporate some weights. You just come and introduce them here in the errors or sort of in the likelihood that comes from each of the individual storms. So this allows you to come and prioritize in your hyperparameter tuning experiments or storms in this case in your database that have specific features. So we can now go and optimize, and then you can sort of figure out what is the accuracy. And in general, for most of the applications, this is not a very challenging problem. Instead of in terms of getting good meta-model accuracy, you can come and get a very good accuracy. You can come and see the comparison between high fidelity and surrogate model predictions, or you can come and look at time series how the predictions look. Like black curve in this case is the exact model. Red one is the mean predictions, and then I also put the plus or minus or one standard deviation by using the predictive variance of Kriging. Now, one of the key questions is, okay, let's say that if you were not given the database, if you were able to come and select the storms for random simulations, how better could you come and do? And the typical way that we would do a design of experiments in this case would be sort of to try to minimize the integrated mean square error. Of course, you can always have some weights where you don't come and look at the entire predictive variance. You can always remove this scaling the process variance outside, and then you can come and sort of look the integrated mean square error only with respect to this a green component here, which is the component that varies within your domain. Like the scaling in front really doesn't matter. And then the key thing here is that because this ultimately doesn't depend on what the new observation is, you can come and now include a new observation and come and figuring out, okay, so this was my initial variance. Let's say what would be the updated variance if I included this new a new storm, a new observation in this specific location. So since you can very easily update that, so this was sort of the initial error. I'm demonstrating here with a two-dimensional example, and this is how the error would be as soon as you include that experiment. You integrate this error over the whole domain, then you can calculate this IMSE criterion, and then of course the idea is that you're going to select the new storm that comes and gives you the biggest utility. In other words, it gives you the biggest reduction or the smallest integrated mean square error when you come and include it in the already existing database. Of course, this is not that easy of a problem to solve. You do have an integration, which generally you can perform through Monte Carlo, and then you have here an optimization that's well known to have multiple local minima. So how we're going to try to address it, at least in our case, we always try to use some random search. But ultimately, the only computational intensive thing, okay, apart from the fact that you do have a Monte Carlo, is coming and inverting this new matrix, but you can very easily come and get this updated matrix inversion by coming and using inversions that you already have in memory. So it's not that computational intensive. The only problem is the Monte Carlo simulation. And generally we can come and exploit some characteristics of the problem to come and decrease a little bit the cost of this optimization. And the whole idea is, let's say that you do a random search, so sort of these are your candidate experiments. Coming probably and adding experiments in domains where the error is small probably is not going to give you great utility. So you can do sort of before coming and calculating this integrated mean square error for all your candidate experiments in the random search. You can come and remove sort of the experiments that belong in already domains where you know that you predict well. So instead, we're only going to keep this green ones, and in this case, for all these green ones, you need to sequentially come and update and figure out what the integrated mean square error is. Sequentially, you have to do it for all. This is sort of the part that takes some computational effort. This is why we introduce this step here to at least reduce how many times we need to get this updated of the integrated mean square error. And after you've done it for all your candidate solutions, you pick the one that gives you the smallest value. And after this point, now you need to go and perform your optimization. You perform the new observations, and then you optimize all the Haber parameters, and of course it does come and give you an updated, estimation of the integrated mean square error, because in this case you assume that I'm not going to change my Haber parameters after I get the new observation, but of course to really optimize your Gaussian process you need to come, to benefit the most of your Gaussian process. As soon as you have the observation, you should go and optimize for the Haber parameters. One slide of how this works, for an increased number of experiments, coefficient of determination, compare 3 different approaches. One is if you naively went and just pick the next, storm, and or if you go and optimize for purposefully for the next storm. And here we have the case where you don't perform the hyperparameter retuning every storm, but you do it in batches. So in this case, you're going to wait until you have 80 new storms before you go and re-optimize. This is because the Army Corps that does these studies always perform the simulations in batches, not one by one. And the difference here, okay, so really this, the difference in the two plots is how exactly I'm measuring my accuracy in terms of what I'm going to use my surrogate model for. This is sort of if there is a uniform prioritization in the entire domain. So in other words, I don't know what I'm going to use the surrogate model for at the point where I'm optimizing it, or maybe I'm going to use it for any possible storm. And this is not if we were specifically we're trying to have some weights in the storm. Sort of this is for real-time risk assessment because you really don't know a priori what the storm is going to be. This is sort of if you try to predict the risk long-term for a region, because in that case, you do have some probabilistic characteristics of what those new storms are going to be about. And you can see that the benefits that you get from this adaptive selection of the storms will be different depending on what you're going to use the surrogate model for. Another and you can see coming here that sort of the comparison about with respect to the benchmark risk, of using surrogate models with different type of storms, like adaptively always selected. You can see that at some point you start and converging, pretty accurately to the exact risk. Actually, the exact risk here is calculated with 600 storms, so we are around with 1/3 of that computational effort. If you are willing to adaptively perform the storm selection, you get almost very accurate estimates along the whole hazard curve. Another interesting point in when you talk about the hurricane risk assessment is this whole idea of climate change, and especially with storm intensification. So because we developed our database for what we think the intensity is going to be right now, in 30 years right now projection is that we're expecting even more intensified hurricane. So we ask a question, okay, how can we come and train a meta model to explicitly try to do extrapolations, and we implemented this in this specific database by separating it into two domains. So we're going to come and assume that we know these storms, and only then we try to sort of, we're going to keep these storms outside of our initial database, and then we're going to try to predict sort of in extrapolating mode. Compare the two different optimization, hyperparameter optimization, MLE or leave one out cross-validation. And the top results here is what happens for interpolation, what happens here for extrapolation, sort of for intensified storms. And you can see that leave one out cross-validation does tend to outperform a maximum likelihood when you talk about extrapolating with your surrogate models. Of course, this is results that it's sort of well understood for people that look into detail and why MLE cannot perform well for in some instances for extrapolative. And of course now we can come, since we know that we're interested in storms that maybe have higher intensity, we can come and use some weights within our existing storms, like these weights here, that come and prioritize these storms. So as soon as we do this, we can come and see that we come and significantly improve our extrapolative capabilities. And on top of that, if we're willing, okay, so we know that we have some future intensification, let's say that we're going to perform like 10 more runs, explicitly targeting that domain, but smartly selected, you can come and see that you can even come and increase your abilities to predict better in extrapolative mode without really coming and impacting a lot your abilities to predict in interpolative mode. Sort of this is for the different intensities of hurricanes, the coefficient of determination when you predict within the hurricane. You can see that as soon as you include these weights and maybe some new storms, you start to significantly better predict for this very high intensity storm. And ultimately, what do these tools allow you to do. They allow you to build a very nice cyber infrastructure to come and help, decision planners to make intelligent decisions during, storm events. So this is something that we developed for the coast of New Jersey. It's a web platform. It can run. It runs on the cloud, but people on the ground, they can use it, especially in their smartphones during an emergency, and you can come in and pretty much use this. It democratizes to some extent access to the computational power that these people don't have. So with these surrogate models that have pre-trained, very efficiently, we can come and give them updated predictions of what they should expecting to be flight or not. So pretty much a user can come, can define any hurricane that they want, or pull it directly from the NOAA predictions, and then the tool within a couple of minutes, it runs an ensemble of 1,000 scenarios and comes and gives predictions of what's going to be the inundation depths along the coast, and they can come and zoom in and sort of because this is also a GIS system, they can come and put all the map or any GIS map that they have locally to superimpose, and that's going to help them a lot try and figuring out, we have here sort of evacuation route that at some point seems to be inundated. We better start moving populations through a different evacuation route. That was the first part of the talk. I think we're doing sort of good in time. I'm going to spend the next 5 minutes going into a little bit of a different mode and talking about some challenges or the need that we have for better data. This is going to be ideas, not solutions, and especially I'm going to focus on this part here in terms of the different sort of scales that the natural hazard problem impacts. One of the big things that we are talking in the natural hazards right now is about community resilience. So we understand that this is sort of the layered hazard exposure. So this is going to be your hazard. This is going to be sort of your individual, buildings, and we can do this fairly well, up to this point. The problem is when you start talking about the impact of the community, you really don't care what happens to the individual building, but you care about how that individual building and also all the other similar buildings that you're going to have really going to impact globally, the community that you're using. Let me give you an example. For example, the damages or the downtime to your hospital, if you just ask the question what's going to happen to that hospital, it's not that relevant. It's really relevant, what's going to happen to that hospital and also in all the surrounding hospitals. If you have a downtime of 10 days of, let's say, critical facility of the hospital, but you have next to you 10 other critical facilities that are intact, that impact is not going to be that significant. But for example, if you're the only critical facility in that region, that's going to have a bigger impact. And we still face the challenge of really having the type of data that we need to come and estimate what are the consequences in that global scale. We can very well predict what's going to be the downtime for the individual hospital. But if we're talking about, what's going to be the impact to the healthcare services along that region, we cannot do it yet. And that's a critical problem, because you can, in order to be able to make intelligent decisions, because really that is what you try to optimize. You don't really try to optimize your individual critical facility, but you try to optimize looking all the network of the critical facilities, what's going to be globally the impact in your region. But even if we talk about the individual building, we still face some challenges because we devise always new metrics that we are interested in. So in the era of sustainability, right now we have started looking at is what is the embodied energy of the materials that we are using, and ultimately we try to make intelligent decisions by coming and looking not only the initial embodied energy, but also the embodied energy of the repairs that material is going to need in the next 15 years. And that is a very, a new type of problem. We can calculate, for example, what's going to be the embodied energy of that wall. Material density and everything else, we know how to do it. But if we come and say, okay, in the next 50 years, we can, predict what type of repairs we're going to need, explicitly coming and quantifying what the embodied energy of those repairs, we cannot do it right now. So the data, it's a lack of data to some extent because we haven't really critically thought of that problem up to now. But it's also, I think, what Stan was talking about. We need an army of graduate students to look over the whole internet and try to find that information. At some point, we need, help from the computer science, ontology, semantic data to be able to, extract that information more efficiently. And one final slide, especially when we're talking, so this is sort of the life cycle of a civil engineering, building. And what is critical for us is a lot of learning from disasters. They don't happen often, but when they happen, as unfortunate as they are, they still give us a unique opportunity to really test our theories and figure out what's happening. This is a great example. This is from Hurricane Matthew in Haiti. I think I'm somewhere here. So these are two identical buildings, and I think the surge that we measured in this area, it's around 5 to 6 meters. One has all the walls blown out, the other is intact. Of course, the wind did have an impact on the roof, but in terms of the surge on the walls, no damages. And we couldn't understand why that happened. They seem to have exactly the same orientation with respect to the coast. So we flew our a drone, and as soon as we saw that image, it was initially not clear, but eventually was clear. It's this patch of vegetation here. So that part of vegetation came and sheltered this building here. So we have a lot to learn from data that we get from disasters, but how exactly we can automate that. For example, if we were not here and we just had a drone flying over or a satellite image, without the civil engineering expert to come and look at the photos, understanding that something interesting has happened here, to come and start investigating a little bit the questions, I don't think we're there yet. In summary, I think resilience to natural hazards is going to be one of the most significant challenges that especially the civil engineering community is going to face for the next century. And generally, computational statistics tool provide unique opportunities to support and enhance decision support. Another problem that we have is generally lack of data for consequence quantification. We can do, multi-criteria design under uncertainty optimization very well. We have the algorithm, have developed all these things, but unless we can quantify exactly what our metrics should be, all these great tools don't have an impact. And always say junk in, junk out. And we do lack, that data for consequence quantification, especially at the community resilience level, but also at the individual component level. And with that, thank you very much for your attention.
Just a quick clarifying question. In the first part, how large is your hyperparameter space? I'm a little bit surprised as a machine learning person that you've went out cross-validation style sweeping works.
So if you have 6 parameters, depending on what correlation function you're going to assume, you can be as low as 6, sort of like the scaling between the dimensions. In this case, that was a generalized exponential correlation function, so 7 hyperparameters.
Okay, so that's big.
No, it's a very low dimensional problem.
So you mentioned, first of all, thank you, very interesting talk. You mentioned some coupling with other types of modeling, for instance, climate predictions or weather. Is there any coupling with social dynamics, what people do during these events?
Yes, that's again, that's another critical component, and sort of do some agent-based modeling that you're going to figure out evacuation trends, and that's also an essential part of trying to do an intelligent decision making. There are actually a lot of people, especially in the hurricane, because there you do have enough, early enough, warning. Also for tsunamis. If you talk in hazard like the earthquakes, I think like there it's a little bit more challenging to be able to model what the reactions are going to be. But for the type of hazard that you do have the early warning, yeah, there is a lot of work from the social side to try and figure out the behavioral response during the evacuation.
Okay, so thank you again.